Hello there, and welcome to the Sleepy Atomist. I'm so grateful you've joined me tonight. Maybe you're lying in bed, soft light fading, your thoughts gently slowing. Or perhaps you're simply letting your mind wander before sleep finds you. However you've arrived, this space is yours, a calm place for quiet science, deep wonder, and a little bedtime magic. Tonight, we begin something extraordinary. A gentle journey to meet a cosmic visitor that has traveled farther than anything you've ever imagined, carrying with it secrets from the depths of interstellar space. Not science fiction aliens or imaginary spaceships, but a real wanderer from beyond our solar system, racing toward us through the cosmic dark. This journey is calm and perhaps a little curious, and I'll do my very best to make it comforting and sleep-inducing. But fair warning, sometimes science is just too beautifully interesting to ignore. If you find yourself a little too awake by the end, I hope at least you'll drift off with a softer mind and something new nestled gently in your thoughts. Before we dive in, a quiet thank you to those who've offered a super thanks or joined the channel as a member. Your kindness helps keep this little pocket of peace growing. And if you feel moved to support in any way, know that it means more than I can say. Now, let's begin. Let's meet the visitor that's coming to call. You wake one morning and check the news, scrolling through the usual stories of earthly events. Politicians debating, weather patterns shifting, markets rising and falling. Everything feels local, terrestrial, contained within the familiar boundaries of our small blue world. But buried in the science section, if you look carefully, you might find a small headline that changes everything. Interstellar visitor approaching solar system. Most people scroll past without a second thought. After all, space news often seems abstract, distant, irrelevant to daily life. But this headline represents something profound. For only the third time in human history, an object from beyond our solar system is paying us a visit. Its name is 3I Atlas, and it carries with it stories from the cosmic deep. Picture Atlas as it appears to our most sensitive telescopes. Not a bright star or dramatic fireball, but a faint, fuzzy dot moving slowly against the background of distant stars. To untrained eyes, it would be invisible, unremarkable, lost among the thousands of other dim objects that populate our sky. But to astronomers who understand what they're seeing, Atlas represents something extraordinary. The 3I in its name tells the story of cosmic rarity. It stands for third interstellar, marking Atlas as only the third confirmed visitor from beyond our solar system. The first was ʻOumuamua in 2017, a mysterious cigar-shaped object that tumbled through our inner solar system and disappeared before we could study it properly. The second was Borisov in 2019, a more cooperative visitor that developed a beautiful tale and allowed months of detailed observation. Now comes Atlas, and with it, the accumulated wisdom of 2 previous interstellar encounters. We know what to look for. We know which telescopes to point where. We know the questions to ask and the measurements to make. Atlas arrives not as a complete mystery, but as the latest chapter in humanity's growing library of interstellar science. You might wonder what makes these objects so special. After all, our solar system contains millions of asteroids and comets, countless chunks of rock and ice that orbit our sun in predictable patterns. What makes an interstellar visitor different? The answer lies in speed and trajectory, in the telltale signatures that reveal an object's true origins. Everything born in our solar system follows certain rules. Planets orbit in roughly the same plane. Comets from the outer reaches of our system approach on highly elliptical paths, but remain gravitationally bound to our sun. Even the most distant objects, those that take thousands of years to complete a single orbit, still follow trajectories that curve back toward our star. But Atlas follows different rules. Its path through our solar system is hyperbolic, meaning it's moving too fast to be captured by our sun's gravity. Atlas is just passing through, like a cosmic tourist taking a brief tour of our stellar neighborhood, before continuing on its journey to other stars. This hyperbolic trajectory is the signature of an interstellar origin, the mathematical proof that Atlas came from somewhere else entirely. The speed tells the same story. Atlas is moving at roughly 30 kilometers per second relative to our Sun, about 67,000 miles per hour. That's fast enough to circle the Earth in under 15 minutes, fast enough to travel from New York to Los Angeles in 3 minutes. But more importantly, it's fast enough to escape our solar system entirely, confirming that Atlas is indeed an interstellar wanderer. Where did Atlas come from? The honest answer is that we don't know for certain. Its trajectory suggests it originated from the general direction of the constellation Lynx, but that doesn't tell us which specific star system gave it birth. The object has been traveling through interstellar space for so long that its original path has been modified by gravitational encounters with other stars, making it nearly impossible to trace back to its source. What we do know is that Atlas has been journeying between the stars for an almost incomprehensible length of time. If it originated from even our nearest stellar neighbour, Proxima Centauri, it would have been travelling for tens of thousands of years to reach us. More likely, it came from much farther away, meaning its journey spans hundreds of thousands or even millions of years. Think about that timeline. Atlas may have begun its journey when early humans were just learning to use fire, when ice ages came and went on Earth like passing seasons, when our planet was an unremarkable world that no one in the galaxy had any reason to notice. During all those eons, Atlas has been drifting through the cold darkness between stars, preserved in the perfect refrigeration of interstellar space. But now, Atlas is approaching the inner solar system, and everything is about to change. As it draws closer to our Sun, the ancient ices that have remained frozen throughout its galactic journey are beginning to warm. Water ice starts to sublimate directly from solid to gas. Carbon dioxide follows suit. Other exotic compounds that don't exist naturally on Earth begin their own transformation from solid to vapor. This warming process will create Atlas's coma, the glowing atmosphere that surrounds the nucleus and makes the object visible to our telescopes. If Atlas contains enough volatile material, it might also develop a tail, streams of gas and dust blown away by the solar wind that could stretch for millions of kilometers across space. But here's where the story becomes beautifully uncertain. We don't know exactly what Atlas will do as it approaches our Sun. Will it brighten dramatically, becoming visible to backyard astronomers with small telescopes? Will it develop a spectacular tail that captures the imagination of millions? Or will it remain frustratingly dim, revealing its secrets only to professional observers with access to the world's largest instruments? The answer depends on Atlas's composition, its size, and how it responds to our Sun's warming influence. Unlike comets born in our solar system, which form from familiar materials under known conditions, Atlas carries the chemistry of an entirely different stellar environment. It might contain ices and organic compounds that behave in unexpected ways when heated by an alien star. This uncertainty is part of what makes Atlas so compelling. Unlike planets, which follow predictable orbits we've calculated for centuries, Atlas represents the universe's capacity to surprise us. It carries with it the mystery of the unknown, the possibility that our assumptions about comets and ice and stellar chemistry might need revision. As you settle into your evening routine, Atlas continues its approach toward the inner solar system. Somewhere beyond the orbit of Jupiter, this ancient wanderer carries within its frozen heart the chemical signature of another star system, the accumulated history of a million-year journey through the cosmic void, and the promise of discoveries yet to come. Whether Atlas becomes a spectacular naked-eye object or remains a telescopic curiosity, its visit represents something profound about our place in the galactic community. We are not isolated in space. The cosmos is dynamic, interconnected, filled with wanderers that carry information between star systems like cosmic messengers. Atlas reminds us that space is not empty but full of travelers, that star systems exchange material across impossible distances, that the universe is far more connected than our everyday experience suggests. In the coming months, as Atlas makes its closest approach to our Sun, we'll have the opportunity to study authentic samples from another star system without ever leaving our own cosmic neighborhood. Tomorrow night, we'll follow Atlas on its incredible journey from the space between stars, discovering how such cosmic wanderers navigate the gravitational landscape of the galaxy and what their presence tells us about the dynamic nature of stellar neighborhoods. But for now, Rest easy knowing that somewhere in the darkness above, a visitor from beyond our solar system carries ancient secrets toward their moment of revelation, when ice from alien worlds will sublimate in the warmth of our sun and whisper stories from the cosmic deep. You stand in your backyard on a clear night, looking up at the familiar constellations. Orion the Hunter marches across the winter sky. The Big Dipper pours starlight into the cosmic dark. Everything appears eternal, unchanging, as predictable as the sunrise. But tonight, something different moves among those ancient patterns of light. It doesn't look like much. Even through a telescope, it appears as nothing more than a faint, fuzzy smudge creeping slowly against the stellar background. No dramatic tail streaming across the heavens, no brilliant nucleus blazing with reflected sunlight, just a dim, grey blob that most people would dismiss as an error or a smudge on the lens. But this unremarkable object carries with it one of the most extraordinary stories in astronomy. It is 3I Atlas, and it has travelled farther to reach this moment than anything else you will ever see with your own eyes. Atlas is an interstellar visitor, only the third such object ever confirmed by human science. While everything else in our night sky was born in our solar system or shines with the light of distant suns, Atlas carries within its frozen heart the chemistry of an alien star system. It is, quite literally, a piece of another world that has come to call. The journey Atlas has taken to reach your backyard telescope is almost impossible to comprehend. If you could somehow follow its path backward through time, you would trace a line across the galaxy that spans distances measured not in millions of miles, but in trillions upon trillions. The object has been travelling through the cold void between stars for longer than human civilization has existed. Picture the galaxy as it was when Atlas began its journey. If the wanderer started travelling 500,000 years ago, it left its home system when our ancestors were just beginning to control fire, when ice ages carved and reshaped the continents, when Earth was an unremarkable planet orbiting an ordinary star that no one in the cosmos had any reason to notice. During all those millennia, Atlas has been drifting through interstellar space, a realm so cold and empty that it makes the most desolate places on Earth seem warm and crowded by comparison. The temperature in the void between stars hovers just a few degrees above absolute zero. The density is so low that a thimble full of interstellar space contains fewer atoms than a single breath of air. Yet Atlas survived this journey intact, preserved by the perfect refrigeration of the cosmic deep. Whatever ice and dust and organic compounds it carried when it left its birth system, all of this material has remained essentially unchanged throughout its galactic wandering. Atlas is a time capsule, carrying authentic samples from another stellar neighbourhood across impossible distances to our curious telescopes. You might wonder what could send an object wandering between the stars. In our solar system, gravity keeps everything in predictable orbits. Planets circle the sun. Moons orbit planets. Even the most distant comets remain gravitationally bound, following elongated paths that eventually bring them back toward our star. But sometimes, rarely, something changes the rules. A close encounter with a giant planet might fling a comet outward at such high speed that it escapes the solar system entirely. A passing star could gravitationally disrupt the outer reaches of a planetary system, sending chunks of ice and rock careening into interstellar space. Or perhaps Atlas was ejected during the chaotic early days of its birth system, when planets were still migrating and gravitational interactions were far more violent than they are today. The moment of Atlas's departure from its home system would have been subtle, almost anticlimactic. No explosion, no dramatic ejection. The object would simply have found itself moving a little too fast, following a trajectory that curved away from everything familiar and into the vast emptiness between worlds. At first, Atlas might have remained within its birth system for years or even decades, slowly gaining distance from its parent star. But eventually, inevitably, it would have crossed the boundary where stellar gravity releases its hold. Atlas would have become truly interstellar, a citizen of the galaxy, rather than any particular star system. The path Atlas followed through the cosmos wasn't straight, Nothing travels in straight lines through space for very long. The gravity of every star it passed would have tugged at it slightly, altering its course by small amounts that accumulated over hundreds of thousands of years. Atlas's journey through the galaxy resembles a complex dance, a trajectory that curves and spirals in response to the gravitational choreography of stellar motions. During its long wandering, Atlas may have passed through stellar nurseries where new suns were being born from collapsing clouds of gas and dust. It might have travelled through the aftermath of supernovae, collecting on its surface atoms forged in the nuclear fires of stellar death. Perhaps it drifted through the quiet regions between spiral arms, where stars are sparse and the darkness is so complete that the galaxy's structure becomes visible, only as a faint glow distributed across the sky. Each environment Atlas encountered would have left its mark, adding layers to its surface composition like tree rings recording different seasons. Cosmic rays, high-energy particles accelerated by magnetic fields and stellar explosions, would have constantly bombarded its surface, slowly altering its chemistry and creating new compounds that don't exist anywhere in our solar system. The interstellar dust Atlas collected during its journey tells stories of cosmic environments we can study without ever leaving our stellar neighborhood. Some of this dust is older than our solar system, formed in the winds of stars that died before our sun was born. Other grains were created in supernova explosions, tiny specks of matter forged in some of the most violent events in the universe. Now, after eons of wandering, Atlas has entered our solar system and begun to feel the growing influence of our sun's warmth. For the first time in hundreds of thousands of years, the ancient ices locked within its structure are starting to respond to stellar radiation. Water ice begins to sublimate directly from solid to gas. Carbon dioxide follows suit. Other exotic compounds that have no earthly equivalent start their own slow transformation. This warming process creates Atlas's coma, the glowing atmosphere that makes interstellar visitors visible to our telescopes. The coma doesn't shine with its own light, like a star. Instead, it glows by reflecting sunlight and fluorescing as solar radiation excites the gas molecules surrounding Atlas's nucleus. If Atlas contains enough volatile material, the warming might also create a tail, streams of gas and dust blown away by the solar wind. This tail wouldn't point backward along Atlas's path of motion, as you might expect. Instead, it would point away from the sun, pushed outward by the pressure of solar radiation and the solar wind's stream of charged particles. But here's where Atlas's story becomes beautifully uncertain. We don't know exactly what will happen as it continues to approach our sun. Will it brighten dramatically, becoming visible to amateur astronomers with backyard telescopes? Will it develop a spectacular tail that captures the imagination of millions? Or will it remain frustratingly dim, revealing its secrets only to professional observers with access to giant instruments? The answer depends on factors we can't yet determine. Atlas's size, its exact composition, the way its alien chemistry responds to our sun's warmth. All of these variables will determine whether this interstellar visitor becomes a memorable spectacle or a subtle scientific treasure, visible only to dedicated observers. Unlike comets born in our solar system, which formed from familiar materials under known conditions, Atlas carries the chemistry of an entirely different stellar environment. It might contain ices and organic compounds that behave in ways we've never observed. Its response to solar heating could surprise us, teaching us new lessons about how matter behaves in the cosmic environment. This uncertainty is part of what makes Atlas so compelling. In an age when we can predict eclipses centuries in advance and calculate planetary positions with extraordinary precision, Atlas represents the universe's capacity for surprise. It reminds us that the cosmos still holds mysteries, still has the power to astonish those patient enough to watch and wonder. As you drift towards sleep tonight, Atlas continues its approach through the outer reaches of our solar system. Every day brings it closer to its moment of maximum visibility, when the warming influence of our sun will fully awaken this ancient wanderer from its million-year slumber. Somewhere in the darkness beyond Jupiter, Atlas carries within its frozen structure the accumulated history of a journey between stars, the chemical signature of another world, and the promise that our solar system is not isolated, but part of a dynamic galactic community where worlds exchange visitors across impossible distances. Tomorrow night, we'll follow Atlas on the specific path it's taking through our solar system, discovering when this interstellar wanderer will make its closest approach to our Sun, and when we might have our best opportunity to witness this visitor from the cosmic deep. But for now, rest knowing that this unremarkable-looking smudge moving slowly across our sky carries within it one of the most remarkable stories in the universe, a tale of cosmic wandering that spans the space between stars and the depths of galactic time. Atlas moves through space at 67,000 miles per hour. That number sounds abstract until you realize it means this cosmic wanderer could travel from New York to Los Angeles in less than 4 minutes. It could circle the entire Earth in under 15 minutes. Yet even at this tremendous speed, Atlas has been traveling for hundreds of thousands of years just to reach our solar system. The distance Atlas has covered defies easy comprehension. If you could somehow stretch a measuring tape along its path through the galaxy, you would need trillions upon trillions of miles to reach from its origin to where it glides through space tonight. Light itself, the fastest thing in the universe, would take centuries to travel the route Atlas has followed. This speed tells us something profound about Atlas's origins. Nothing born in our solar system moves this fast, relative to the Sun. Our planets orbit at predictable speeds. Earth travels around the Sun at about 67,000 miles per hour. But that's orbital motion, following a closed path that brings us back to the same place each year. Atlas's speed is different. It's escape velocity, the speed needed to break free from gravitational bonds entirely. Atlas achieved this speed through violence, though not the dramatic explosion you might imagine. More likely it was flung from its birth system through a gravitational slingshot, effect perhaps during a close encounter with a giant planet, or when a passing star disrupted the outer reaches of its original solar system. The ejection would have been gentle by cosmic standards, but decisive. One day, Atlas was a member of an alien solar system. The next, it was an exile, sentenced to wander the galaxy forever. The path Atlas followed through space wasn't straight. Gravity doesn't allow straight lines over cosmic distances. Every star the wanderer passed would have tugged at it slightly, bending its trajectory by small amounts that accumulated over geological time. Atlas's route through the galaxy resembles a complex curve, spiraling through three-dimensional space in response to the gravitational influences of thousands of stars. During its journey, Atlas traveled through environments that don't exist in our solar system. It may have passed through stellar nurseries where massive stars were being born, regions so energetic that they glow with the light of stellar formation visible across galactic distances. The radiation in these areas would have bathed Atlas in high-energy photons, possibly altering its surface chemistry in ways we're only beginning to understand. Atlas might also have drifted through the aftermath of stellar death. When massive stars exhaust their fuel, they explode as supernovae, events so violent they can briefly outshine entire galaxies. These explosions scatter newly forged elements through space, enriching the interstellar medium with the carbon, oxygen, iron, and other heavy elements necessary for rocky planets and life. Atlas may have collected some of these atoms on its surface, carrying samples of stellar nuclear synthesis from across the galaxy. The space between stars isn't empty, though it's emptier than any vacuum we can create on Earth. It contains roughly 1 atom per cubic centimetre, mostly hydrogen left over from the Big Bang. But it also holds more complex structures, dust grains formed in stellar winds, organic molecules created in the cold depths of molecular clouds, even primitive life forms that some scientists believe might survive the journey between worlds. Atlas swept through this tenuous material for eons, collecting it on its surface like a cosmic snowball, gathering flakes during an endless winter. Some of the dust grains now coating Atlas are older than our solar system, formed in stars that died before our Sun was born. Others were created more recently in the winds of red giant stars or the explosive deaths of white dwarfs. The cosmic rays Atlas encountered during its journey left their own signatures. These high-energy particles, accelerated by supernova shocks and stellar magnetic fields, constantly bombarded the wanderer's surface. Unlike the gentle radiation that warms Earth, cosmic rays carry enough energy to break apart molecules and rearrange atoms. Over hundreds of thousands of years, they slowly altered Atlas's surface composition, creating new compounds that exist nowhere in our solar system. Temperature during Atlas's journey remained constant at just a few degrees above absolute zero. In the depths of interstellar space, far from any warming star, chemical reactions essentially stop. Time becomes irrelevant for anything except radioactive decay. Atlas existed in the universe's perfect deep freeze, its composition locked in the state it achieved when it left its birth system. This cryogenic preservation means Atlas carries within its structure authentic samples from another stellar environment. When our telescopes analyze its spectrum in the coming months, they'll be reading a chemical signature that formed around an alien sun, perhaps in conditions quite different from those that created our own solar system. Atlas also collected information during its travels. The proportions of different isotopes in its structure reflect the stellar nucleosynthesis processes that occurred in its birth system. The organic compounds it contains might reveal how carbon chemistry develops in other parts of the galaxy. Even the cosmic dust coating its surface carries data about the interstellar environments it passed through. Some regions of the galaxy would have been more dangerous for a wandering object. Near the galactic center, where stars are packed more densely and a supermassive black hole dominates the gravitational landscape, Atlas might have experienced close encounters that dramatically altered its course. The intense radiation environments near massive stars could have stripped away some surface material, while the gravitational chaos of dense stellar clusters might have flung it in entirely new directions. Other regions would have been quieter, vast spaces between spiral arms where stars are sparse and the interstellar medium is thinner. In these cosmic deserts, Atlas could have traveled for tens of thousands of years without passing near any significant gravitational influence, drifting through a darkness so complete that the galaxy's spiral structure would have been visible only as a faint architectural glow distributed across the sky. The timing of Atlas's arrival in our solar system represents an almost impossible coincidence. Of all the moments in the galaxy's 13 billion-year history, when it could have wandered through our stellar neighborhood, it chose now during the brief period when intelligent life on Earth has developed the technology to detect and study interstellar visitors. Think about the precision required for this cosmic encounter. Atlas began its journey from some distant star system hundreds of thousands of years ago, following a trajectory determined by gravitational influences it experienced along the way. Meanwhile, our solar system continued its own orbit around the galactic center, moving through space at over 500,000 miles per hour. The fact that these two paths intersected at precisely the moment when humanity can recognize and analyze interstellar objects represents a convergence of astronomical proportions. Atlas's approach to our solar system marks the end of one phase of its existence and the beginning of another. For eons, it has been a citizen of interstellar space, shaped by cosmic rays and coated with alien dust. But now, as it feels the growing influence of our sun's gravity and warmth, Atlas is about to undergo a transformation that will reveal secrets locked away since it left its birth system. The warming has already begun, though it remains subtle. As Atlas approaches the inner solar system, the ancient ices that have stayed frozen throughout its galactic wandering are starting to respond to solar radiation. Water ice begins to sublimate directly from solid to gas. Carbon dioxide ice follows. Other compounds that don't exist naturally on Earth start their own gradual transformation. This process will create Atlas's coma, the glowing atmosphere that makes interstellar visitors detectable to our telescopes. Unlike the solid surface of a planet or asteroid, this coma consists of gas and tiny dust particles liberated from Atlas's nucleus as it warms. The coma doesn't generate its own light, but shines by reflecting sunlight and fluorescing as solar radiation excites the gas molecules. Tomorrow night, we'll explore the precise timing of Atlas's journey through our solar system, discovering when this interstellar wanderer will make its closest approach to our sun, and what that means for observers hoping to catch a glimpse of this visitor from the cosmic deep. But for now, let Atlas's incredible journey remind you that space is not empty, but full of wanderers, that the galaxy is not static, but dynamic, constantly exchanging material between star systems across distances that challenge human comprehension. Atlas represents the universe's capacity for connection across impossible scales, carrying messages from one stellar neighborhood to another through the patient persistence of cosmic time. Atlas will reach its closest approach to the Sun on January 13th, 2025. Mark that date in your mind because it represents the culmination of a journey that began when our ancestors were learning to make the first stone tools, when ice sheets covered continents, when Earth was an unremarkable planet that no intelligence in the galaxy had any reason to notice. January 13th, 2025. The date sounds ordinary, like any other day on the calendar, but for Atlas, it will be the most significant moment in hundreds of thousands of years of cosmic wandering. On that day, this ancient traveler will reach perihelion, its point of closest approach to our star, coming within about 180 million kilometers of the Sun's surface. To put that distance in perspective, Atlas will pass closer to our Sun than Earth's orbit. It will be inside the realm where our planet circles each year, experiencing solar radiation more intense than anything it has felt since leaving its birth system eons ago. For a brief cosmic moment, Atlas will be our neighbor, sharing the same region of space that has nurtured life on Earth for billions of years. The approach isn't sudden. Atlas has been falling toward this appointment for months already, accelerating as our Sun's gravity pulls it deeper into the inner solar system. Right now, as you rest in the quiet of night, Atlas is crossing the orbital path of Mars, still months away from its closest approach, but already beginning to feel the increasing warmth of solar radiation. Every day brings Atlas closer to its rendezvous with the Sun. Every day, the solar flux striking its surface grows stronger. The ancient ices that have remained frozen since the wanderer left its birth system are beginning their slow awakening, starting the process that will transform Atlas from a dark, cold chunk of interstellar material into a glowing beacon visible to telescopes around the world. But January 13th represents more than just Atlas's closest approach to the Sun. It also marks the beginning of the end of this interstellar visitor's time in our solar system. After perihelion, Atlas will begin its outward journey, accelerating away from our Sun as gravity converts the energy of its inward fall into outward velocity. Within months, it will cross the outer boundaries of our solar system and return to the cold darkness between stars. The timing creates a window of opportunity that astronomers have been planning for since Atlas was first discovered. Unlike Oumuamua, which caught observers by surprise and disappeared before detailed studies could be completed, Atlas has given us advance notice. Telescopes around the world are already pointed in its direction, tracking its approach and analyzing the light it reflects and emits. The best viewing conditions will occur in the weeks surrounding perihelion, when Atlas is closest to the Sun and potentially brightest. But there's a catch that makes observation challenging. As Atlas approaches its closest point to our star, it will also appear closer to the Sun in our sky, making it difficult to observe against the bright background of solar radiation. Imagine trying to see a distant candle flame while staring into a spotlight. That's the challenge astronomers face when observing objects near the Sun. The overwhelming brightness of our star creates a zone of sky where even powerful telescopes struggle to detect faint objects. Atlas will spend several weeks passing through this region of difficult observation. The exact timing of Atlas's visibility depends on several factors that remain uncertain. Its brightness will determine how close to the Sun it can be observed before solar glare overwhelms the signal. Professional observatories with specialized coronagraphs might be able to track Atlas even when it's very close to the Sun, but amateur astronomers will need to wait for the object to move away from our star's glare. Atlas's orbit through our solar system follows a precise mathematical curve determined by the laws of celestial mechanics. Unlike a planet, which follows a closed elliptical orbit that brings it back to the same location periodically, Atlas travels on an open hyperbolic trajectory. It approaches the Sun, makes a sharp turn around our star, then heads back out toward interstellar space, never to return. The shape of this trajectory resembles a branch of a mathematical hyperbola, a curve that approaches a straight line as it extends toward infinity. Atlas entered our solar system on one branch of this curve and will exit on the other, its path bent by the sun's gravity but never captured into a closed orbit. Orbital mechanics dictates that Atlas will move fastest when it's closest to the sun. During perihelion passage, the wanderer will be racing through space at nearly 90 kilometers per second, over 200,000 miles per hour. That's fast enough to travel from Earth to the Moon in less than 2 hours, fast enough to cross the entire diameter of our planet in 3 minutes. This tremendous speed means Atlas will spend relatively little time in the inner solar system, where it's easiest to observe. The object will zip through the orbital zone of the inner planets in a matter of months, then spend years slowly receding toward the outer boundaries of our solar system's influence. The orbital geometry also determines which parts of Earth will have the best views of Atlas during different phases of its visit. As the wanderer moves through our solar system, its position relative to Earth's orbit changes constantly. Sometimes it will be visible in the pre-dawn sky, sometimes in the evening hours after sunset, sometimes not visible at all from certain locations on Earth. Astronomers have calculated these viewing geometries with extraordinary precision. They know exactly where Atlas will appear in the sky on any given date, which constellations it will pass through, and when it will be best positioned for observation from different latitudes on Earth. This predictive power allows observers to plan their campaigns months in advance. But there's one crucial factor that all the orbital calculations can't predict: how bright Atlas will become. Brightness depends on the object's composition, its size, and how its surface materials respond to solar heating. These properties remain largely unknown, making Atlas's visibility a beautiful uncertainty. If Atlas contains large amounts of volatile ices like water and carbon dioxide, the warming effect of solar radiation could cause dramatic outgassing that creates a substantial coma and possibly a visible tail. The sublimating gases would reflect and scatter sunlight, potentially making Atlas bright enough to see with binoculars or even the naked eye. Alternatively, if Atlas has a composition similar to asteroids with little volatile material, it might remain relatively faint throughout its passage. Professional telescopes would still be able to track and study it, but the object might never become bright enough for casual observation by amateur astronomers. The uncertainty extends to Atlas's size, which affects how much surface area is available for solar heating. A larger object would sublimate more material and potentially become brighter, while a smaller one might remain frustratingly dim even at closest approach. Some computer models suggest Atlas could reach a brightness comparable to the brighter stars visible to the naked eye. Others predict it will remain a telescopic object throughout its visit. The only way to find out is to wait and watch as the ancient wanderer approaches its appointment with our sun. Weather on Earth adds another layer of uncertainty to Atlas observations. Clear skies will be essential for tracking this relatively faint object, but weather patterns are notoriously difficult to predict months in advance. Astronomers are already making backup plans, identifying multiple observing sites in different climatic zones to maximize the chances of capturing good data during Atlas's brief visit. The timing of Atlas's passage also coincides with winter in Earth's northern hemisphere, when many of the world's major observatories experience their worst weather. Snow, clouds, and storms could interfere with observations at crucial moments, making Atlas's visibility as much a matter of terrestrial weather as cosmic mechanics. International cooperation will be essential for maximizing the scientific return from Atlas's visit. As the object moves through its orbit, it will be visible from different parts of Earth at different times. Observatories in Australia might have the best view during one phase of the passage, while telescopes in Chile or Hawaii are better positioned for other observations. Professional astronomers are coordinating their efforts to ensure continuous coverage of Atlas throughout its approach, perihelion passage, and departure. This global network of observers will track the wanderer's brightness, analyze its spectrum, and monitor any changes in its activity as solar heating takes effect. Amateur astronomers are also preparing for Atlas's visit, setting up equipment and learning the sky positions where the object will appear. While professional observatories have the advantage of large apertures and sophisticated instruments, amateur observers often have the flexibility to respond quickly to unexpected changes in Atlas's brightness or activity. As you settle into sleep tonight, Atlas continues its inexorable approach toward January 13th. Every hour brings it closer to that moment when it will feel the full warmth of our sun for the first time in hundreds of thousands of years. The cosmic clock is counting down toward a rendezvous that represents the convergence of ancient wandering and modern observation, of interstellar journey and human curiosity. Tomorrow night, we'll explore how astronomers track Atlas's approach and predict its behavior, discovering the detective work that allows us to follow this cosmic wanderer across the vast distances of the solar system. But for now, rest knowing that time itself is bringing this ancient visitor closer to its moment of revelation, when the warming touch of our sun will awaken secrets that have been frozen since Atlas left its birth system and began its epic journey between the stars. A telescope dome opens in the Chilean desert. Inside, a massive mirror begins tracking a point of light so faint it's invisible to human eyes. The observer at the controls has never seen Atlas directly, never laid eyes on this ancient wanderer, yet knows exactly where to point the instrument. This is modern astronomy's greatest magic trick, finding needles in the cosmic haystack using nothing but mathematics and patience. Atlas was discovered not by accident, but through systematic hunting. Astronomers don't just stumble across interstellar visitors. They find them by photographing the same patches of sky repeatedly, then comparing the images to detect objects that move against the stellar background. It's like playing a cosmic game of spot the difference, except the differences are often so subtle they require computer analysis to detect. The discovery image probably looked unimpressive. Atlas would have appeared as nothing more than a faint dot, barely distinguishable from background noise. But that dot was moving, and its motion told a story that experienced observers knew how to read. The speed and direction of movement across the sky contained clues about the object's distance, its orbit, and ultimately its origin. 3 observations are enough to determine a preliminary orbit for any solar system object. The first observation gives you a position and time. The second, taken hours or days later, provides the object's apparent motion across the sky. The third observation allows astronomers to calculate whether that motion follows a predictable curve or represents something more exotic. For Atlas, those early orbital calculations revealed something extraordinary. The object wasn't following a closed elliptical path like a typical comet or asteroid. Instead, its trajectory was hyperbolic, meaning it was moving too fast to be gravitationally bound to our sun. This mathematical signature immediately identified Atlas as an interstellar visitor, only the third such object ever confirmed. But, confirming, interstellar origin is just the beginning of the detective work. Astronomers then face the challenge of determining where Atlas came from, what it's made of, and what it might do as it approaches our sun. Each piece of information requires different observational techniques and careful analysis of subtle signals. Spectroscopy provides the most detailed information about Atlas's composition. When sunlight reflects off the object's surface, it carries with it the fingerprints of whatever materials are present. Different compounds absorb and reflect light at specific wavelengths, creating distinctive patterns that astronomers can decode like a cosmic barcode. The spectrum of reflected sunlight from Atlas reveals which minerals might be present on its surface. Silicate rocks, metallic compounds, and organic materials each leave their own signatures in the reflected light. By comparing Atlas's spectrum to laboratory measurements of known materials, astronomers can make educated guesses about what this interstellar visitor is made of. But Atlas's spectrum also contains information about its journey through space. Cosmic rays and solar wind have been bombarding its surface for hundreds of thousands of years, potentially altering its composition in ways that don't occur naturally in our solar system. The spectroscopic signatures might reveal these space-weathering effects, providing clues about how long Atlas has been wandering between the stars. Photometry, the precise measurement of Atlas's brightness, tells another part of the story. As the object rotates, different parts of its surface reflect varying amounts of sunlight toward Earth. These brightness variations reveal Atlas's rotation period and give hints about its shape and surface properties. Most asteroids and comets rotate with periods measured in hours. Atlas's rotation, when finally determined, will provide clues about its history. A very slow rotation might indicate that Atlas has been tumbling through space for so long that collisions with interstellar dust have gradually slowed its spin. A rapid rotation could suggest a more recent ejection from its birth system. The brightness measurements also reveal how Atlas responds to solar heating. As the object approaches our sun, any volatile ices on its surface should begin to sublimate, creating a coma of gas and dust that makes the object appear larger and potentially brighter. Monitoring these changes allows astronomers to infer what kinds of ices Atlas contains and how they respond to warming. Astrometry, the precise measurement of Atlas's position against the stellar background, allows astronomers to refine the object's orbit with extraordinary precision. Each new observation provides another data point that helps constrain the mathematical description of Atlas's path through our solar system. These position measurements are accurate to tiny fractions of an arcsecond, angles so small they're like measuring the width of a human hair from several miles away. This precision is necessary because small errors in position translate to large uncertainties in predicting where Atlas will be months in the future. The orbit calculations also work backward in time, allowing astronomers to trace Atlas's path through the outer solar system and determine when it first entered our Sun's sphere of influence. These retrograde calculations can reveal when Atlas crossed the heliopause, the boundary where our Sun's solar wind gives way to the interstellar medium. But tracking Atlas's motion through our solar system is only part of the detective work. Astronomers also want to know where this wanderer came from originally. Tracing its trajectory back through the galaxy requires accounting for the gravitational influences of nearby stars and the galaxy's rotation. This galactic archaeology is complicated by the fact that Atlas has been traveling for so long that its original path has been modified by multiple stellar encounters. Every time the wanderer passed near another star, that star's gravity would have bent its trajectory slightly. Over hundreds of thousands of years, these small deflections accumulate into significant course changes. Computer simulations can work backward through these gravitational encounters, calculating the probable effects of stellar close approaches and estimating what Atlas's path might have looked like before it entered our solar system. But the uncertainties grow larger the farther back in time the calculations extend. Some models suggest Atlas might have originated from the general direction of the constellation Lynx, but that doesn't identify a specific parent star. The wanderer could have been ejected from any of dozens of stellar systems in that region of the sky, or it might have followed such a complex path through the galaxy that its current direction of approach bears little resemblance to its original trajectory. Ground-based telescopes around the world are coordinating their observations to track Atlas's approach from multiple angles. Different observatories have different strengths. Some excel at photometry, others at spectroscopy, still others at astrometric precision. By combining data from multiple telescopes, astronomers can build a more complete picture of this interstellar visitor. Space-based telescopes add another dimension to the detective work. Above Earth's atmosphere, these instruments can observe wavelengths of light that don't penetrate to ground level. Ultraviolet and infrared observations from space-based platforms might reveal spectroscopic features invisible to ground-based telescopes. The Hubble Space Telescope, despite its age, remains one of the most powerful tools for studying small, faint objects like Atlas. Its sharp images can resolve details invisible to ground-based telescopes, while its spectrographs can analyze the object's composition with high precision. Hubble observations of previous interstellar visitors provided crucial data about their properties and behavior. Amateur astronomers also contribute to the Atlas detective story. While professional observatories focus on detailed spectroscopic and photometric studies, amateur observers often provide valuable monitoring data. Their observations help track Atlas's brightness changes and can provide early warning if the object suddenly becomes more active than expected. The coordinated effort to study Atlas represents one of astronomy's greatest strengths, the ability to combine observations from around the world to tackle problems too complex for any single observatory. As Atlas approaches its closest encounter with our Sun, this global network of professional and amateur observers stands ready to capture every photon of information the ancient wanderer has to offer. Predicting Atlas's behavior as it warms up remains one of the biggest challenges in the detective story. Computer models can estimate how different types of ices might respond to solar heating, but Atlas's alien composition might behave in unexpected ways. The only way to know for certain what will happen is to watch and wait as the cosmic drama unfolds. Weather adds another layer of uncertainty to the observational campaign. Cloud cover, atmospheric turbulence, and seasonal weather patterns all affect the quality of ground-based observations. Astronomers are already developing backup plans and identifying multiple observing sites to maximize the chances of capturing good data during Atlas's brief visit. As you drift towards sleep tonight, this cosmic detective story continues to unfold. Around the world, telescopes track Atlas's approach, while computers process the data and update orbital predictions. Every observation adds another piece to the puzzle of this ancient wanderer's identity and history. The detective work will intensify as Atlas draws closer to perihelion. In the coming weeks, astronomers will watch for the first signs of activity as solar heating begins to affect the object's surface. Those early observations will provide crucial clues about what Atlas is made of and how spectacular its closest approach to our Sun might become. Tomorrow night, we'll explore the eyes that will watch Atlas's approach, discovering which telescopes around the world are best equipped to study this interstellar visitor and what they hope to learn from its brief passage through our cosmic neighborhood. But for now, rest knowing that the cosmic detective story continues, with each new observation bringing us closer to understanding this ancient messenger from the space between stars and the secrets it carries from its epic journey across the galaxy. The Atacama Desert stretches across northern Chile, one of the driest places on Earth. Here, where rain might not fall for years at a time, the world's most powerful telescopes stand sentinel against the cosmic dark. Tonight, as you rest in the comfort of your home, these mechanical giants prepare to turn their gaze toward a faint speck of light carrying secrets from another star system. The Very Large Telescope perches on Cerro Paranal, its 4 8-meter mirrors working in concert to gather ancient photons from Atlas. Each mirror is larger than a school bus, polished to such perfection that if scaled up to the size of Earth, the largest imperfection would be only 6 feet tall. These mirrors will collect light that has bounced off Atlas's surface after traveling across more than 100 million miles of space. But the VLT is just one member of a global army of instruments preparing to study this interstellar visitor. In Hawaii, the twin Keck telescopes on Mauna Kea point their 10-meter mirrors toward the same patch of sky. In Spain, the Gran Telescopio Canarias adds its 10th 4-meter eye to the watch. Each telescope brings unique capabilities to the hunt for Atlas's secrets. Space provides an even better vantage point for studying faint objects like Atlas. The Hubble Space Telescope, orbiting high above Earth's atmosphere, can capture images with a sharpness impossible from the ground. Hubble's vision isn't limited by atmospheric turbulence, the constant shimmer of air that blurs even the best ground-based observations. The James Webb Space Telescope adds infrared vision to the arsenal. While our eyes see visible light, Webb detects the infrared radiation that objects emit as heat. If Atlas begins to warm up as it approaches the Sun, Webb's sensitive infrared detectors might be among the first to notice the telltale signatures of sublimating ice and outgassing material. Each telescope sees the universe differently. Optical telescopes like Hubble capture the same wavelengths of light visible to human eyes, revealing Atlas as it appears in reflected sunlight. Radio telescopes detect the long wavelength radiation that gas molecules emit when excited by solar radiation. X-ray telescopes search for the high-energy signatures that might indicate unexpected activity on Atlas's surface. The challenge of observing Atlas lies not just in its faintness, but in its motion. Unlike stars, which appear fixed in their positions over human timescales, Atlas moves noticeably against the stellar background from night to night. Telescopes must track this motion precisely, adjusting their pointing continuously to keep the wanderer centered in their field of view. Modern telescopes accomplish this tracking through computer control systems that can predict Atlas's position with extraordinary accuracy. The orbital calculations performed by astronomers translate into precise pointing coordinates that guide each telescope's motors. As Atlas moves across the sky, the telescopes follow like patient hunters tracking elusive prey. Spectroscopy provides the most detailed information about what Atlas is made of. When sunlight reflects off the object's surface, it carries with it the chemical fingerprints of whatever materials are present. Spectrographs attached to large telescopes spread this reflected light into its component wavelengths, creating detailed rainbow patterns that reveal Atlas's composition. Different compounds absorb and reflect light at specific wavelengths, creating distinctive patterns in the spectrum. Water ice leaves its signature at certain infrared wavelengths. Carbon dioxide creates different absorption features. Organic compounds produce complex spectral patterns that can reveal the presence of molecules containing carbon, hydrogen, oxygen, and nitrogen. The spectrum of Atlas will tell astronomers whether this interstellar visitor resembles comets from our own solar system or contains exotic materials that formed under alien conditions. The relative strengths of different spectral features can reveal not just what compounds are present, but in what proportions, providing a detailed chemical inventory of matter from another star system. Photometry, the precise measurement of brightness, requires different techniques than spectroscopy. Photometric observations use sensitive electronic detectors to measure the exact amount of light reaching the telescope from Atlas. These measurements can detect brightness changes as small as a few percent, revealing information about the object's rotation, shape, and activity level. As Atlas rotates, different parts of its surface reflect varying amounts of sunlight toward Earth. If one side of the object is brighter than the other, perhaps due to different surface materials or ice deposits, this will show up as periodic brightness variations. The timing of these variations reveals Atlas's rotation period. The brightness measurements also provide early warning of increased activity as Atlas approaches the Sun. If volatile ices begin to sublimate from the surface, they will create a coma of gas and dust around the nucleus. This coma reflects additional sunlight, making Atlas appear brighter and larger than its solid nucleus alone. Some telescopes specialize in rapid photometry, taking measurements many times per second to catch brief flashes or sudden changes in brightness. If Atlas experiences outbursts of activity as it warms up, these rapid observations might capture the events as they happen, providing real-time information about how interstellar material responds to solar heating. Astrometry, the precise measurement of position, requires the most accurate telescopes and careful calibration against background stars. These observations determine Atlas's exact location in the sky at specific times, data that astronomers use to refine the object's orbital calculations and predict its future position. The precision required for astrometric observations pushes the limits of ground-based telescopes. Atmospheric turbulence constantly shifts the apparent positions of celestial objects by tiny amounts. Advanced telescopes use adaptive optics systems with flexible mirrors that adjust hundreds of times per second to compensate for atmospheric distortion. Space-based telescopes avoid atmospheric effects entirely, making them ideal for the most precise astrometric measurements. The Gaia spacecraft has revolutionized stellar astrometry by measuring the positions of billions of stars with unprecedented accuracy. While Gaia focuses on mapping our galaxy's stellar population, its techniques could be applied to tracking objects like Atlas. International cooperation multiplies the power of individual telescopes. As Atlas moves across the sky, it will be visible from different parts of Earth at different times. Observatories in Chile might have the best view during one phase of the object's approach, while telescopes in Hawaii or Spain are better positioned for other observations. Coordinating these observations requires careful planning and communication between observatory teams around the world. Astronomers must schedule telescope time months in advance, predict when Atlas will be best positioned for observation from each site, and ensure that the most important measurements aren't missed due to bad weather or technical problems. Amateur astronomers add another dimension to the observational campaign. While they can't match the light-gathering power or spectroscopic capabilities of professional telescopes, amateur observers often have the flexibility to respond quickly to unexpected changes in Atlas's brightness or activity. Networks of amateur astronomers can provide continuous monitoring that complements the more detailed but intermittent observations from professional observatories. If Atlas suddenly brightens or develops visible activity, amateur observers around the world can track these changes and alert professional astronomers to point their larger telescopes at the object. The challenge of observing Atlas will intensify as the object approaches perihelion. When Atlas is closest to the Sun, it will also appear close to our star in Earth's sky, making observations difficult due to solar glare. Only the most sophisticated telescopes with specialized coronagraphs will be able to track Atlas during its closest solar approach. This creates a race against time for astronomers. The period when Atlas is brightest and most active will also be when it's most difficult to observe. Telescopes must gather as much data as possible during the weeks leading up to perihelion, knowing that the object might become temporarily unobservable just when it's most interesting. Weather adds uncertainty to every observational campaign. Clear skies are essential for ground-based telescopes, but weather patterns are notoriously difficult to predict. Astronomers are already identifying backup observing sites in different climate zones to maximize the chances of capturing good data despite local weather conditions. Cloud cover during crucial observations could mean missing once-in-a-lifetime opportunities to study Atlas's behavior. This uncertainty drives the emphasis on international cooperation and multiple observing sites. If clouds block the view, from one observatory, others might still have clear skies. The data collected by all these telescopes will flow into computer databases, where astronomers can combine observations from multiple instruments to build a complete picture of Atlas. Different telescopes contribute different pieces of the puzzle. Spectroscopy reveals composition, photometry tracks, brightness changes, astrometry refines the orbit. Modern astronomy depends on this kind of collaborative observation. No single telescope can capture all the information needed to fully characterize an object like Atlas. Only by combining data from multiple instruments, each with its own strengths, can astronomers hope to understand this interstellar visitor. As you settle into sleep tonight, telescopes around the world continue their patient watch. Automated systems track Atlas's motion across the star fields, while sensitive detectors collect every photon of reflected sunlight. The mechanical eyes that never blink, never tire, never lose focus, maintain their vigil through the night. Each observation adds another piece to the growing database of information about this ancient wanderer. Every spectrum reveals new details about its composition. Every brightness measurement tracks its activity level. Every position measurement refines predictions about its future behavior. Tomorrow night, we'll explore what Atlas might be made of and how its alien composition could differ from the familiar materials found in comets and asteroids born in our solar system. But for now, rest knowing that the eyes in the dark continue watching, gathering ancient light from a visitor that has traveled longer and farther than anything else we'll ever observe, preparing to decode the secrets it carries from the space between stars. Atlas hangs in the dark between Jupiter and Mars, a dirty snowball no bigger than a mountain, yet it carries within its frozen heart the chemistry of an alien star system. To understand what makes this interstellar visitor unique, you must first understand what comets are and how they form in the cold outer reaches of planetary systems. Comets are not solid rocks like asteroids. They are collections of ice, dust, and organic compounds that condensed in the frigid zones far from their parent stars. Think of them as cosmic fossils, preserving unchanged samples of the materials from which planetary systems form. Every comet carries within its structure a record of the chemical conditions that existed during its birth. In our solar system, most comets formed in two distinct regions. The Kuiper belt, beyond Neptune's orbit, birthed the short-period comets that return every few decades or centuries. The Oort cloud, a vast spherical shell of icy objects surrounding our solar system, spawned the long-period comets that take thousands of years to complete their orbits around the Sun. These comets contain the building blocks of worlds: water ice that could fill oceans, carbon dioxide that could create atmospheres, and complex organic molecules that might seed the chemistry of life. When comets strike planets during the early history of a solar system, they deliver these essential ingredients to worlds that might otherwise remain barren. Atlas formed in similar conditions around an alien star, but its composition might differ dramatically from our solar system's comets. The chemistry available during planetary formation depends on the type of star, the composition of the original nebula, and the specific conditions of temperature and pressure that existed in that distant system. The nucleus of a typical comet measures only a few kilometers across, but this small size conceals remarkable complexity. The interior might contain layers of different materials, like geological strata recording different epochs of formation. Some regions might be rich in water ice, while others contain more exotic compounds that freeze only at extremely low temperatures. Atlas's surface probably resembles fresh asphalt, darkened by cosmic rays and organic compounds that have been altered by millions of years of radiation exposure. This dark coating, called a lag deposit, forms when surface ices sublimate away, leaving behind dust and non-volatile materials that don't easily evaporate. Beneath this dark crust lies the active material that will determine how spectacular Atlas becomes as it approaches our Sun. Water ice makes up the bulk of most comet nuclei, but frozen carbon dioxide, methane, ammonia, and other compounds contribute to the complex chemistry. Each type of ice sublimates at different temperatures, creating a sequence of activity as solar heating intensifies. The first ices to respond to solar warming are the most volatile compounds like carbon monoxide and methane. These substances can begin sublimating while a comet is still beyond Jupiter's orbit, creating faint coma activity that might be detectable only by the most sensitive instruments. As the comet draws closer to the Sun, water ice begins to sublimate, dramatically increasing the brightness and size of the coma. Atlas's alien origin means it might contain ices that don't exist in our solar system. Different stellar environments could produce exotic compounds that freeze only under specific conditions. The relative abundances of different elements might also differ significantly from solar system norms, creating unusual ice mixtures that behave unpredictably when heated. The sublimation process that creates a comet's coma and tail is more violent than it might appear. As ices change directly from solid to gas, they expand by factors of hundreds or thousands, creating tremendous internal pressure within the comet nucleus. This pressure can crack the surface, expose fresh ice, and sometimes trigger explosive outbursts that dramatically brighten the comet. Jets of gas and dust can erupt from specific locations on the nucleus, where active ice deposits lie close to the surface. These jets often follow the comet's rotation, creating spiral patterns in the coma and tail that reveal details about the nucleus's spin and internal structure. High-resolution images of comet nuclei show landscapes carved by these violent sublimation processes. The dust mixed throughout Atlas's icy matrix tells its own story. This material might include silicate grains similar to those found in meteorites, but it could also contain exotic minerals that formed under different stellar conditions. Some dust grains might be older than our solar system, preserved unchanged since they condensed in the winds of dying stars. Organic compounds add another layer of complexity to comets like Atlas. These carbon-based molecules can form through various processes in the cold depths of space. Some might have condensed directly from the gas phase in the original stellar nebula. Others could have formed through radiation-induced chemistry during the long journey through interstellar space. The organic inventory of comets includes simple molecules like methane and more complex compounds like amino acids, and even primitive proteins. These molecules represent some of the most sophisticated chemistry possible under the extreme conditions of space. Atlas might carry organic compounds that evolved under different stellar conditions, providing samples of alien biochemistry. The internal structure of Atlas remains largely unknown, but computer models suggest that comet nuclei are not uniform. Instead, they might contain distinct regions with different compositions, perhaps reflecting different epochs of formation or varying conditions within the original nebula disk. Some models propose that comet nuclei are loose collections of smaller chunks, held together by weak gravity and frozen ices. This rubble pile structure could explain why some comets fragment when they approach the Sun, breaking apart under the stress of differential heating and internal pressure from sublimating gases. Atlas's density probably lies somewhere between solid ice and fluffy snow. Measurements of other comet nuclei suggest densities much lower than solid rock, indicating that these objects contain significant empty space between loosely packed particles. This low density makes comets particularly susceptible to disruption by tidal forces or internal pressure. The rotation of Atlas will affect how it responds to solar heating. If the object tumbles chaotically, different parts of its surface will be heated at different times, creating complex patterns of activity. If it rotates regularly around a stable axis, heating will be more predictable, with activity concentrated in regions that face the Sun most directly. Temperature variations across Atlas's surface will create a complex mosaic of sublimation activity. Areas that receive direct sunlight might reach temperatures sufficient to sublimate water ice, while regions in permanent shadow remain frozen. The boundary between these zones will shift as Atlas rotates and as its distance from the Sun changes. The magnetic field carried by the solar wind will interact with the ionized gases in Atlas's coma, potentially accelerating charged particles and creating phenomena visible only at specific wavelengths. These interactions might reveal details about the composition of Atlas's coma that aren't accessible through other observational techniques. Atlas's response to solar heating will depend not only on its composition, but also on its thermal properties. How quickly heat penetrates into the nucleus determines whether sublimation occurs only at the surface or extends deeper into the interior. This thermal behavior affects the total amount of material that Atlas can release and how long its activity might persist. The dust released from Atlas will carry important information about the conditions in its birth system. Different minerals form under specific temperature and pressure conditions, so analyzing the dust composition can reveal details about the environment where Atlas originally condensed from the stellar nebula. Some of the most scientifically valuable information about Atlas will come from studying isotope ratios in its released gases. Isotopes are versions of the same element with different numbers of neutrons. The relative abundances of different isotopes depend on the nuclear processes that occurred in Atlas's parent star, providing direct information about stellar nuclear synthesis in another part of the galaxy. As Atlas approaches perihelion, it will begin to reveal these secrets through the language of sublimated gas and liberated dust. Each molecule that escapes from its nucleus carries information about conditions in an alien stellar system, preserved unchanged during hundreds of thousands of years of interstellar wandering. The anatomy of this cosmic visitor represents more than just scientific curiosity. Atlas is a messenger from another world, carrying authentic samples from a stellar environment we'll never visit. Its composition might reveal whether the chemistry of planetary formation is universal or whether different stellar conditions produce dramatically different outcomes. As you drift towards sleep tonight, Atlas continues its approach toward the Sun, its frozen anatomy preparing for the warming that will transform it from a dark, inactive nucleus into a glowing beacon visible to telescopes around the world. Tomorrow night, we'll explore what might happen as Atlas awakens from its million-year slumber, discovering how solar heating could transform this ancient wanderer into one of the most spectacular objects in our sky. But for now, rest knowing that Atlas carries within its icy heart the chemistry of another world, waiting to share its secrets with any civilization curious enough to watch and wonder at its cosmic revelation. Atlas is invisible to your naked eyes tonight, hidden in the darkness beyond Mars, too faint for anything but the most powerful telescopes to detect. But in the coming weeks, this ancient wanderer might transform itself from an unremarkable speck into one of the brightest objects in our sky. The key word is might, because no one knows for certain what will happen when Atlas feels the full warmth of our Sun. The brightening process has already begun, though it remains subtle. As Atlas draws closer to our star, solar radiation strikes its surface with increasing intensity. The dark, frozen crust that has protected its interior for hundreds of thousands of years is starting to warm, and somewhere beneath that protective layer, ancient ices are beginning their slow awakening. Water ice requires significant heating before it sublimates directly from solid to gas. At the temperatures Atlas currently experiences, water remains firmly frozen, but other compounds are more sensitive to warmth. Carbon monoxide ice can begin sublimating while a comet is still beyond Jupiter's orbit. Methane and nitrogen ices respond to even gentler heating. These early stages of activity might already be occurring deep within Atlas's nucleus. Gases might be percolating through the porous interior, building pressure beneath the dark surface crust. If enough gas accumulates, it could eventually break through weak points in the crust, creating the first visible signs of cometary activity. The initial brightening might be so gradual that only sensitive instruments can detect it. Atlas's brightness could increase by small percentages over days or weeks before human eyes notice any change. Professional astronomers monitor these subtle variations constantly, watching for the first signs that this interstellar visitor is responding to solar heating. But if Atlas contains substantial amounts of volatile ice, the brightening could accelerate dramatically once it begins. Sublimation is a positive feedback process. As gas escapes from the nucleus, it carries away dust and debris that darken the surface. This exposure of fresh, clean ice to sunlight increases the sublimation rate, which exposes more ice, which increases the rate further. The result can be a runaway brightening that transforms a faint telescopic object into a spectacular naked-eye comet within days or weeks. Comet Hale-Bopp demonstrated this process in the 1990s, brightening from invisibility to brilliant prominence as it approached the Sun, and developed one of the most magnificent cometary displays in human history. Atlas might follow a similar path, though its alien composition introduces uncertainty into any predictions. Interstellar objects carry chemistry from stellar environments that might differ significantly from our solar system's conditions. Exotic ice mixtures could behave in unexpected ways when heated by our Sun's radiation. The coma will be the first visible sign of Atlas's awakening. As gas escapes from the warming nucleus, it creates an atmosphere around the solid core that can grow to enormous size. Some comets develop comas larger than the planet Jupiter, vast spheres of tenuous gas and dust that glow by reflecting sunlight and fluorescing under solar ultraviolet radiation. Atlas's coma might be visible through binoculars weeks before the object becomes bright enough for naked-eye observation. The coma appears as a fuzzy, star-like glow that distinguishes comets from the sharp points of light created by stars and planets. This fuzzy appearance has been noted by astronomers for millennia, giving comets their name from the Greek word for hairy star. The composition of Atlas's coma will provide crucial information about this interstellar visitor's interior chemistry. Different gas molecules emit light at specific wavelengths when excited by solar radiation. Spectrographs can identify these emission lines, creating a detailed inventory of the gases escaping from Atlas's nucleus. Water vapor typically dominates the coma of solar system comets, but Atlas might surprise us with unusual compositions. If it formed around a different type of star or under different chemical conditions, it could release gases rarely seen in our local comets. Exotic molecules might create spectral features that challenge astronomers' interpretation. The dust component of the coma adds another dimension to Atlas's potential brightness. As gas escapes from the nucleus, it entrains tiny particles of solid material that have been mixed throughout the ice matrix. This dust reflects sunlight efficiently, often contributing more to a comet's total brightness than the gas component. Atlas's dust might differ significantly from solar system materials. Different stellar environments could produce exotic minerals or unusual grain compositions that reflect light in unexpected ways. The color of the reflected light might reveal information about the dust's composition and the conditions under which it formed. If Atlas develops substantial activity, it might also grow a tail, one of the most spectacular features any comet can display. Cometary tails form when the solar wind, a stream of charged particles flowing from the Sun, pushes gas and dust away from the coma. The tail always points away from the Sun, regardless of the comet's direction of motion. Gas tails and dust tails often appear as separate structures with different characteristics. Gas tails tend to be blue and narrow, composed of ionized molecules accelerated to high speeds by magnetic forces in the solar wind. Dust tails appear yellowish and broader, made of tiny particles that follow more complex trajectories under the combined influence of solar gravity and radiation pressure. Atlas might develop multiple tails with different orientations and colors, creating a complex structure that evolves as the object moves through its orbit. The exact appearance would depend on the relative amounts of gas and dust released, the size distribution of the dust particles, and the interaction between Atlas's coma and the solar wind. The brightness of a fully developed comet depends on several factors that remain unknown for Atlas. The size of the nucleus determines how much surface area is available for sublimation. The composition affects which ices sublimate at different distances from the Sun. The internal structure influences how efficiently heat penetrates into the nucleus. Optimistic predictions suggest Atlas could become as bright as the brightest stars in our sky, possibly even rivaling Venus in its brilliance. If the object contains large amounts of easily sublimated ice and develops substantial coma and tail structures, it could become a spectacular naked-eye object, visible even from light-polluted cities. More conservative estimates suggest Atlas will remain a binocular or small telescope object throughout its passage. If the nucleus is small or composed primarily of less volatile materials, it might brighten modestly, but never become prominent enough for casual observation by amateur astronomers. The uncertainty extends to the timeline of any brightening. Some comets begin developing significant activity while still far from the Sun, allowing months of observation as they approach perihelion. Others remain relatively dormant until the final weeks before closest approach, then suddenly burst into prominence. Atlas's interstellar origin adds another layer of unpredictability. Previous interstellar visitors have behaved differently from solar system comets. ʻOumuamua remained frustratingly faint throughout its passage, never developing the bright coma that would have revealed its composition. Borisov behaved more like a typical comet, developing a visible coma and tail that allowed detailed study. Weather on Earth will play a crucial role in any attempts to observe Atlas's potential brightening. The object's closest approach to the Sun will occur during winter in the Northern Hemisphere, when many observatories face challenging weather conditions. Clouds, snow, and storms could interfere with observations at the most crucial moments. The timing of Atlas's brightening will determine which parts of Earth have the best views. If the object becomes bright, while positioned in the morning sky, observers in certain latitudes will have advantages over others. The celestial mechanics of Atlas's orbit create windows of opportunity that favor different geographic regions at different times. Light pollution presents another challenge for observing a potentially bright Atlas. While the object might become visible from cities if it reaches sufficient brightness, the full beauty of any coma and tail structures would only be apparent from dark sky locations far from urban light pollution. Professional astronomers are preparing for all possibilities, from spectacular brightening to continued faintness. Telescope time has been allocated for intensive monitoring campaigns that will track Atlas's brightness and activity level regardless of how dramatic its awakening might be. Amateur astronomers around the world are also preparing, setting up equipment and learning the sky positions where Atlas will appear. If the object does brighten significantly, millions of people might have the opportunity to see an authentic visitor from interstellar space with their own eyes. The potential for spectacular brightening creates excitement among both professional and amateur astronomers, but it also emphasizes the uncertainty inherent in studying interstellar visitors. Atlas carries within its nucleus the potential for one of the most remarkable cometary displays in recent memory, or it might remain a faint curiosity visible only to dedicated observers with sophisticated equipment. As you settle into sleep tonight, Atlas continues its approach toward the inner solar system, carrying within its frozen heart the ingredients for potential transformation. Whether it becomes a brilliant beacon or remains a modest telescopic object, Atlas represents our best opportunity to study authentic material from another star system. Tomorrow night, we'll explore what Atlas might teach us about ice and chemistry in alien stellar environments, discovering how this interstellar wanderer could revolutionize our understanding of planetary formation throughout the galaxy. But, for now, rest knowing that somewhere in the darkness beyond Mars, an ancient visitor carries the possibility of awakening into one of the most spectacular sights our sky can offer, waiting to reveal whether the chemistry of distant worlds can create beauty visible across the void between stars. Somewhere in the darkness beyond Mars, Atlas carries within its frozen heart water that has never known an earthly ocean, carbon dioxide that has never floated in an earthly atmosphere, and organic molecules that condensed around an alien star before our sun was born. Tonight, we chase this ancient ice back to its origins, following a trail of chemistry that spans the galaxy and tells stories about worlds we'll never visit. The ice locked within Atlas isn't ordinary frozen water like you find in your freezer. It's primordial ice, unchanged since it condensed in the outer reaches of an alien solar system hundreds of thousands of years ago. Every molecule preserves the chemical signature of stellar nucleosynthesis that occurred in a different stellar environment, under different conditions, perhaps around a different type of star entirely. When Atlas formed in its birth system, the composition of available materials depended on the nuclear history of its parent star. Stars create heavy elements through fusion reactions in their cores, then distribute these elements through stellar winds and eventual death. The relative abundances of carbon, oxygen, nitrogen, and other elements available during planetary formation reflect this stellar chemistry. Our solar system formed from material enriched by multiple generations of stellar death and rebirth. The Sun is considered a third-generation star, meaning it formed from gas and dust that had already been processed through previous stellar cycles. This history determined the composition of comets and asteroids that formed in our system's outer reaches. Atlas might tell a different story. If it formed around a younger star with less stellar processing in its history, the ice could contain different ratios of heavy elements to hydrogen and helium. If it came from a stellar environment dominated by different types of supernovae or stellar winds, the isotope ratios might differ dramatically from solar system norms. Isotopes provide the most detailed fingerprints of stellar nucleosynthesis. These are atoms of the same element with different numbers of neutrons, created by different nuclear processes in stellar cores. The ratio of deuterium to hydrogen, for example, reflects conditions during the Big Bang and subsequent stellar processing. Carbon-12 to carbon-13 ratios reveal details about the nuclear burning that occurred in massive stars. When Atlas begins to sublimate as it approaches our Sun, these isotope signatures will be released into space where telescopes can analyze them. Spectrographs sensitive enough to detect different isotopes of the same element will read the nuclear history written in Atlas's ancient ice, providing direct information about stellar evolution in another part of the galaxy. The organic compounds within Atlas might represent the most exotic chemistry of all. In the cold depths of space, carbon atoms can link together to form complex molecules that would be impossible under earthly conditions. Some of these compounds might be familiar from studies of solar system comets, but others could represent entirely new forms of carbon chemistry. Amino acids, the building blocks of proteins, have been detected in several solar system comets. If Atlas contains similar compounds, they might have different structures or proportions than those found locally. The discovery of alien amino acids would provide direct evidence that the chemistry of life develops along different pathways in different stellar environments. Even more exotic would be the discovery of compounds that don't exist naturally anywhere in our solar system. Different stellar conditions could promote the formation of carbon chains, aromatic rings, or complex molecules that represent entirely new forms of organic chemistry. Atlas might carry samples of biochemistry that evolved under alien conditions. The water ice in Atlas tells its own story about planetary formation. The isotope ratios in cometary water provide clues about the temperature and chemical conditions that existed when the ice originally condensed. Heavy water, containing deuterium instead of ordinary hydrogen, forms preferentially under certain conditions and can reveal details about the thermal history of Atlas's birth system. Different stellar environments might produce water ice with dramatically different deuterium ratios. If Atlas formed around a cooler star, or in a system with different chemical abundances, its water ice might carry isotope signatures that immediately identify its alien origin. These measurements would provide direct confirmation that Atlas truly originated beyond our solar system. The carbon dioxide ice in Atlas might contain even more exotic information. This molecule forms through different pathways depending on the available chemistry and environmental conditions. The carbon and oxygen isotope ratios in Atlas's CO2 could reveal whether it formed through processes similar to those in our solar system or through entirely different chemical routes. Complex organic molecules frozen within Atlas might include compounds that represent intermediate steps in the development of life's chemistry. If these molecules evolved over millions of years in interstellar space, they might have reached levels of complexity not seen in solar system materials. Atlas could carry samples of prebiotic chemistry that developed under different conditions than anything on Earth. The study of ancient ice from interstellar space also provides information about the environment Atlas traveled through during its galactic journey. As the Wanderer moved between star systems, it would have collected material from the interstellar medium, including gas and dust from stellar winds, supernova explosions, and the general galactic environment. This collected material would be mixed with Atlas's original composition, creating a chemical record of its journey through different galactic neighborhoods. By analyzing the layers of material built up on Atlas's surface, astronomers might be able to trace its path through various stellar environments and determine which regions of the galaxy it has visited. The age of Atlas's ice presents another fascinating question. While the object itself might be hundreds of millions or even billions of years old, some of the ice it contains could be even more ancient. If Atlas incorporated material from the interstellar medium during its journey, some components might date back to the earliest epochs of stellar formation in our galaxy. Studying this ancient ice requires sophisticated analytical techniques that push the limits of current technology. Mass spectrometers sensitive enough to distinguish between different isotopes must analyze tiny amounts of material released from Atlas's nucleus. The signals are often weak and contaminated by terrestrial atmospheric contributions that must be carefully subtracted. Ground-based telescopes contribute to this analysis through high-resolution spectroscopy that can detect the emission lines of specific molecules and isotopes in Atlas's coma. Space-based instruments avoid atmospheric interference and can observe wavelengths that don't penetrate to Earth's surface, providing access to spectral features invisible to ground-based observers. The timing of these observations will be crucial. As Atlas approaches perihelion, different types of ice will sublimate in sequence based on their volatility. The most sensitive compounds will begin outgassing while Atlas is still far from the Sun, while more refractory materials might not become active until the final weeks before closest approach. This sequential release means that telescopes will sample different components of Atlas's interior chemistry at different times during its approach. Early observations might reveal information about the most volatile compounds, while later observations could access materials from deeper within the nucleus that require more heating to sublimate. The data collected from Atlas's ancient ice will be compared to similar measurements from solar system comets to identify similarities and differences. Any compounds or isotope ratios that don't match solar system norms would provide strong evidence for Atlas's interstellar origin and reveal details about chemical processes in other stellar environments. Computer models help interpret these observations by simulating how different stellar conditions would affect the chemistry available during planetary formation. By comparing Atlas's measured composition to predictions for different types of stellar environments, astronomers can constrain the conditions that existed in its birth system. The study of ancient ice from Atlas represents more than just scientific curiosity. This material carries information about stellar nuclear synthesis, planetary formation, and organic chemistry that occurred in a completely different stellar environment. It provides direct samples of matter from another world without requiring interstellar travel. Every molecule that sublimates from Atlas's nucleus carries with it the history of nuclear processes that occurred in an alien star, the chemical conditions that existed during planetary formation in that system, and possibly the evolutionary pathways that led to complex organic chemistry under different environmental conditions. As you drift towards sleep tonight, Atlas continues its journey toward the inner solar system, carrying within its frozen matrix the accumulated chemistry of another world and the environments it passed through during its epic journey between the stars. The ancient ice locked within this interstellar wanderer represents a direct connection to stellar processes that occurred in distant parts of the galaxy, preserved unchanged by the perfect refrigeration of interstellar space and delivered to our telescopes by the patient persistence of cosmic time. Tomorrow night, we'll explore when and where Atlas will be visible to observers on Earth, discovering the window of opportunity when this ancient visitor will reveal its secrets to anyone with the patience to watch and the curiosity to wonder. But for now, rest knowing that the chemistry carried by Atlas spans the galaxy and the eons, connecting our small world to the vast processes of stellar birth and death that have shaped the composition of matter throughout the cosmos. January arrives cold and clear in the northern hemisphere. You step outside on a winter morning and notice Venus shining brilliantly in the pre-dawn sky, the same eastern direction where Atlas will soon make its appearance. In just a few weeks, That same patch of sky might host one of the most remarkable objects visible from Earth, an authentic visitor from the space between stars. The window for observing Atlas opens gradually, like curtains being drawn back to reveal a cosmic stage. Right now, the interstellar wanderer remains too faint for visual observation, detectable only by professional telescopes with sensitive electronic cameras. But as it approaches perihelion on January 13th, Atlas will brighten steadily, potentially becoming visible to increasingly modest equipment. The first observers to catch sight of Atlas will likely be experienced amateur astronomers with large telescopes and detailed star charts. They'll know exactly where to look, following the precise coordinates calculated by orbital mechanics. Atlas will appear as nothing more than a faint, fuzzy star that moves slowly against the stellar background from night to night. But if Atlas contains substantial amounts of volatile ice, this modest beginning could transform into something spectacular. As solar heating intensifies, the ancient wanderer might develop a visible coma that makes it obvious even to casual sky watchers. The transformation from telescopic curiosity to naked eye spectacle could happen within days or weeks. The timing creates both opportunity and challenge for Earth-based observers. Atlas will reach its closest approach to the Sun during January, when it's potentially brightest, but also positioned near our star in the sky. This proximity to the Sun creates a narrow window between when Atlas becomes bright enough to see and when solar glare makes observation impossible. Morning skies offer the best initial viewing opportunities. As Atlas approaches perihelion, it will rise before sunrise in the eastern sky, visible for a few hours before dawn brightens the horizon. Observers willing to rise early will have the first opportunities to witness this interstellar visitors' potentially dramatic awakening. The constellation Hercules provides the backdrop for Atlas's initial appearance, though the object will move steadily across the sky as it follows its hyperbolic orbit through the inner solar system. Star charts showing Atlas's predicted path allow observers to anticipate where to look on any given date, though the exact brightness remains beautifully uncertain. Binoculars might provide the perfect tool for Atlas observation. These instruments combine portability with enough light-gathering power to reveal objects invisible to the naked eye. If Atlas develops a substantial coma, binoculars will show the fuzzy cometary appearance that distinguishes it from the sharp points of light created by stars and planets. Small telescopes will reveal even more detail, potentially showing the structure of Atlas's coma and any tail development. Telescopes with tracking mounts can follow Atlas's motion across the sky, allowing extended observation and detailed study of any changes in brightness or appearance.